So let's work an example with Gaussian random variables where we use information about its probability density function. So let's deal with the random variable x, and this is a Gaussian random variable. And we are told that the probability density function for this Gaussian random variable has the form of 1 over k times square root of 2 pi e to the minus x minus 3 quantity squared over 8. So this is the PDF we're going to work with, and we're going to answer a variety of questions related to this Gaussian random variable. The first thing is, what is the value for k? So you notice in the description of the probability density function there's this unknown quantity k sitting there. So what is k? We can figure that out easily just by recalling what the general form for a Gaussian random variable PDF is. And the general form is 1 over sigma times square root of 2 pi e to the minus x minus the mean squared over 2 sigma squared. So if we rewrite the PDF that we have in this form, we see that we have a 1 over k times square root of 2 pi, so that matches up very nicely with the 1 over sigma square root of 2 pi. And then when I write the exponential term, instead of writing it as divided by 8, I'll actually factor out a 2, because in the general form there's a 2 sigma squared. So I'm going to write it as x minus 3 quantity squared over 2 times 2 squared, because that fits the general form of 2 times sigma squared very nicely. And then by looking at this, now I can tell that sigma has to be 2. So if sigma is 2, then that means the k out front has to be equal to sigma. So I've deduced that k has to be equal to 2. So there's just a little problem to kind of get us warmed up to figure out what k has to be based on what we know the general form that a Gaussian random variable's PDF has to take. So we have k equals 2. So next question. Let's compute the probability that this Gaussian random variable is greater than 2. So remember, we know that the mean of our random variable is 3, and the standard deviation is 2. So we can compute this, the probability that x is greater than or equal to 2. What is that? Well, in terms of the PDF, here's a little sketch of the PDF. The PDF is this Gaussian bell-shaped curve. It's centered at 3 because the mean is 3. And it has a spread that's proportional to the standard deviation or variance. And what we're being asked to compute is really this area. The probability density function, if we integrate it, tells us probabilities. So if I integrate from 2 to infinity, that gives me the probability that the random variable x is greater than or equal to 2. So this area is really what I'm computing. And this is exactly what the Q function easily lets me compute. So I can just plug into my Q function Q of 2 minus the mean divided by sigma. So anytime you deal with a Gaussian random variable and you want to know that the probability of that random variable is greater than or equal to a number, you can use the Q function, and all you do is evaluate the Q function at the number that you're looking at. In this case it's 2, subtract off the mean, and divide by sigma. So that's easy to do. We can simplify this. 2 minus 3 is a negative 1. So this is q of a negative half. But we know that the q function of a negative x is equal to 1 minus q of x. So we can kind of invert this and write 1 minus q of a half. And then if we go look in our table for the q function, we see that the q function at 0.5 is equal to 0.3085. So this quantity is equal to 0.6915. So that area that we shaded in blue is equal to 0.6915, and that seems like a reasonable answer. If I had integrated the entire PDF, I would have gotten 1. If I had integrated from just 3 up to infinity, I would have gotten 0.5. So the fact that I integrated something in between there and got a number in between 1 and 0.5 seems like a reasonable answer. Let's do another example. Let's compute the probability that x is less than or equal to 3. So again, in terms of our PDF, we could compute this by integrating the PDF for all values less than 3, negative 3. So if I integrated from minus infinity up to a negative 3, the probability that I'm looking for is represented by this shaded area here. So just from this cartoon sketch, we would assume or guess that this probability is going to be less than the probability that we computed in part B, just because the area that we've shaded is so much smaller. So this probability of x being less than or equal to negative 3 is equal to 1 minus the probability, 1 minus the probability that x is greater than or equal to 3. So instead of computing x less than or x less than or equal to negative 3, I could also just compute the probability that x is greater than or equal to 3 and then do 1 minus it. And the reason we like this a little better is because this is what the Q function tells us. So let's go ahead and compute this probability. 1 minus p of x greater than or equal to negative 3 is 1 minus Q function, because that's what the Q function does. The Q function tells us the probability that our random variable x is greater than or equal to negative 3 when we're dealing with a Gaussian random variable. So I put a negative 3 there. I have to subtract off the mean and divide by sigma again. So this is equal to 1 minus Q of minus 6 over 2, which is equal to 1 minus Q of negative 3, which is equal to 1 minus 1 of Q of 3. So if you only have Q functions tabulated for positive values, you can use the identity that Q of negative x is equal to 1 minus Q of x, just like we did in part B. So I get 1 minus 1 plus Q of 3, and continuing to simplify, this turns into Q of 3. So if I go look that up, in my Q function table, I get 0.00135, which is a fairly small number for the answer. And again, this seems like a reasonable answer because the cartoon I kind of sketched to begin the problem shows that that area is a pretty small area, much smaller than the area we had for part B. So it seems like this is a reasonable answer. In both of these problems, where you're using the Q function to compute areas underneath the probability density function. And when you're working with Gaussian random variables, this is a very common thing to do to compute desired probabilities, because the Q function is a frequently tabulated function. If you're doing digital communication problems, you probably have a table of this in your textbook. Your calculator might have it. MATLAB has it as a function call. So it's a very widely used function and a very useful function to compute probabilities for Gaussian random variables.